The most powerful locomotive is rarely the most important one. On railroads, reliability matters more than power. That idea feels obvious today, but for decades, railroads had to learn it the hard way. In the previous videos, we followed steam locomotives as they pushed deeper into extremes. We saw machines that produced more power than big boy. We saw turbine locomotives attempt to fix steam through advanced engineering. And we saw how economics ultimately decided the outcome. But power and cost weren't the only forces shaping railroad decisions. There was another factor that mattered just as much: reliability. Because railroads don't operate one train at a time, they operate entire networks. And in a network, a single failure doesn't stay isolated. It spreads. A locomotive that fails doesn't just stop one train. It disrupts schedules, it ties up crews, it blocks tracks, it delays other trains behind it. That is why railroads eventually stopped asking one question: how strong is this locomotive? And started asking another: how often can this locomotive be trusted to run? Power is easy to understand. You add cylinders, you increase boiler pressure, you build a bigger engine. Reliability is harder. Reliability doesn't come from size, it comes from control. A locomotive that produces enormous power is impressive, but a locomotive that produces predictable performance is valuable. Railroads learned that difference through experience. A powerful locomotive that fails once a week is a liability. A less powerful locomotive that runs every day is an asset. That distinction shaped every major railroad decision in the mid-20th century. Because failure costs more than weakness. On a railroad, failure is never just mechanical. When a locomotive fails on the main line, the consequences cascade. The train stops, the crew waits, dispatchers reroute traffic, other trains slow down or stop entirely. Yards begin to back up, schedules slip, customers notice, and customers remember. Freight railroads don't sell horsepower. They sell reliability. They sell the promise that freight will arrive on time, consistently, week after week. Every unexpected failure breaks that promise. That is why railroads measure reliability not as a technical metric, but as a business risk. One failure can erase the profit from dozens of successful runs. And steam locomotives failed in ways that were difficult to predict. Steam was powerful, but it was sensitive. It relied on heat, pressure, and human judgment all working together. Boilers expanded and contracted every day. Metal fatigued. Valves drifted out of adjustment. Bearings wore unevenly. Two steam locomotives of the same class could behave very differently. One might run smoothly for days. Another might develop leaks, hot bearings, or mechanical issues without warning. Railroads tried to manage this variability through maintenance, daily inspections, frequent servicing, large shop forces. But maintenance itself introduced downtime. Steam locomotives spent a significant portion of their lives not moving trains. They were raising steam, cooling down, being inspected, being repaired. From a reliability standpoint, that mattered, because a locomotive that isn't available cannot be reliable. Availability became inseparable from reliability, and steam struggled with both. Railroads noticed that their most powerful steam locomotives were often their least predictable. As designs grew larger and more complex, the margin for error shrank. Higher pressures meant greater stress. More moving parts meant more failure points. Tighter tolerances meant less forgiveness. When something went wrong, it often went wrong quickly. This was especially true on long runs and heavy grades. A failure at the wrong place could block an entire subdivision. Helper engines had to be dispatched, crews timed out, traffic backed up for miles. From the outside, steam failures looked like isolated incidents. From the inside, they were system disruptions. Railroads began to understand that reliability wasn't just a property of the locomotive. It was a property of the entire operation, and steam made that operation fragile. Diesel locomotives approached the problem differently. They were not designed to maximize peak output. They were designed to minimize surprises. Diesel engines started quickly. They warmed up faster. They operated within narrower temperature ranges. They didn't rely on boilers that expanded and contracted under extreme conditions. They didn't require constant manual intervention to stay within safe limits. Most importantly, diesel locomotives behaved consistently. A diesel unit on Monday behaved much like it did on Friday. That predictability changed how railroads operated. Dispatchers could plan with confidence. Schedulers could tighten timetables. Managers could reduce buffers that had once been necessary to absorb steam failures. Reliability created efficiency at the system level. And once railroads experienced that, they were unwilling to give it up. Another critical difference was how failures were handled. When a steam locomotive failed, the solution was rarely simple. The locomotive itself had to be repaired, often on site, or towed to a shop. Until that happened, the train was stranded. Diesel locomotives changed that logic. If a diesel unit failed, it could be isolated. Another unit could take its place. The train could continue moving. This modular approach transformed reliability from a mechanical problem into a logistical one. Railroads didn't need perfect locomotives. They needed systems that could absorb imperfections. Diesel made that possible. Steam did not. Reliability also reshaped labor. Steam locomotives depended heavily on skilled crews. Engineers and firemen constantly adjusted the machine. Fuel, water, pressure, and timing all required attention. Human error was always a factor. Fatigue mattered. Experience mattered. Conditions mattered. Diesel locomotives reduced that dependency. They simplified operation. They automated many tasks. They reduced the number of variables crews had to manage. That made performance more consistent across shifts and crews. Consistency is reliability, and reliability reduces risk. From a management perspective, diesel locomotives were easier to trust. By the time railroads reached the 1950s, the pattern was clear. The locomotives that impressed rail fans were not the locomotives that impressed railroad accountants. The engines that delivered record horsepower were not the engines that delivered dependable service. Railroads didn't abandon power. They simply stopped treating it as the primary goal. Instead, they optimized for uptime, for predictability, for systems that worked day after day, without drama. That shift explains why diesel locomotives spread so quickly once the transition began. And it explains why steam, despite its power, could not compete. Reliability didn't just change which locomotives railroads bought. It changed how railroads planned everything. Once diesel locomotives proved they could run consistently, railroads began redesigning their operations around that assumption. Schedules became tighter, buffers became smaller, networks became more efficient. With steam, railroads had always planned for failure. Extra time was built into schedules. Extra crews were held in reserve. Extra locomotives were stationed as insurance. Those redundancies were expensive. Diesel locomotives allowed railroads to remove them. Because when locomotives run predictably, uncertainty shrinks. And when uncertainty shrinks, costs fall. Planning is where reliability creates its greatest value. A railroad timetable is not just a list of departures and arrivals. It is a promise. Every missed slot creates ripple effects. A late freight train can delay passenger service. A stalled train can block an entire corridor. A missed connection can idle yards and terminals. Steam locomotives made those disruptions more likely, not because they were poorly designed, but because they were sensitive systems. Small issues could escalate quickly. A leaking valve, a hot bearing, a pressure imbalance. Any of those could force a stop. Diesel locomotives reduced that fragility. They didn't eliminate failure. They reduced its frequency and severity, and that distinction mattered more than absolute performance. Reliability also allowed railroads to standardize. Steam-era railroads operated fleets of highly specialized machines. Different classes, different parts, different maintenance procedures. Shops had to support enormous variety. Training was complex. Spare parts inventories were large. Knowledge was fragmented. Diesel locomotives encouraged uniformity, fewer models, shared components, standard maintenance cycles. Standardization made reliability scalable. A reliable system is valuable. A reliable system that can be replicated across an entire network is transformative. Diesel locomotives made that possible. Steam locomotives resisted it. This shift also changed how railroads thought about power itself. Under steam, power was concentrated in a single machine. If you needed more power, you built a bigger locomotive. That increased risk. When a single massive locomotive failed, everything stopped. Diesel locomotives distributed power, Multiple units could be combined, loads could be adjusted, failures could be isolated. This reduced the consequences of any single breakdown. Reliability improved not because diesels never failed, but because failures mattered less. That is a crucial distinction. Railroads learned that resilience is more valuable than raw strength. As diesel fleets expanded, the economic feedback loop became impossible to ignore. Reliable locomotives reduced delays. Fewer delays reduced penalties. Fewer penalties improved customer confidence. Improved confidence attracted more business. More business justified further investment in diesel fleets. Steam locomotives were left outside that loop. Even well-maintained steam engines could not match diesel reliability at scale. The gap widened every year. By the mid-1950s, railroads were no longer debating whether diesel was better. They were debating how quickly steam could be removed without disrupting service. This explains why steam disappeared so fast once the transition began. From the outside, it looked abrupt. From inside railroad management, it was overdue. Steam locomotives demanded constant attention. Diesel locomotives delivered consistent results. Railroads did not have the luxury of nostalgia. They had contracts to fulfill, schedules to meet, margins to protect. Reliability was not a preference. It was a requirement. And this brings us back to the core lesson of this entire series. Steam locomotives did not lose because they were underpowered. They did not lose because engineers stopped innovating. They did not lose because diesel was more exciting. Steam lost because railroads became systems, and systems reward reliability above all else. Power impresses, reliability sustains. That is why railroads chose reliability over power. In the next video, we'll take this idea even further, because reliability is only one part of the cost equation. Hidden beneath steam's daily operation were expenses most people never see. Costs that accumulated quietly, costs that didn't show up in horsepower ratings, costs that ultimately made steam impossible to justify. Railroads didn't abandon power. They learned that reliability is what keeps trains moving.